Hi everyone. So in our last video, we learned about logarithms and how to evaluate them. So in this video, we're going to be looking at functions that incorporate logarithms, and those functions are called logarithmic functions. So the main focus of this video is going to be on what the graphs of logarithmic functions look like. So kind of like when we learned about exponential functions, becoming familiar with the general shape of logarithmic functions and where they have asymptotes, things like that. So what is a logarithmic function? Well, a logarithmic function is a function of the form f of x is equal to log base b of x, where that number b, which we talked about in the last video, is referred to as the base of the logarithm. That number b has to be a positive real number. So no negative numbers allowed for that number b, no zero allowed for that number b. And then additionally, that number b cannot be equal to 1. So you might remember that when we defined exponential functions, similarly, we said that the base of the exponential functions had to be positive, right? It couldn't be 0, it couldn't be negative, and then it also couldn't be 1. And so we'll see later on why we have that connection. So an example of a logarithmic function would be something like f of x is equal to log base 3 of x. So how does this kind of function work? Well, you use it just like any other function, right? So if we wanted to evaluate something, like let's say you wanted to evaluate f of 9, you would take log base 3 of 9. And we learned how to evaluate things like this in our last video, right? And so log base 3 of 9 is just asking you what power do you have to raise 3 to get 9? And the answer is 2. And so for the function log base 3 of x, if the input is 9, the output is 2, and so the graph of this function would contain the point 9, 2. Another example of a logarithmic function would be ln of x, right? So we learned in our last video that ln is a special number, or it's a special logarithm where e is the base. So when we write ln, it's just shorthand for saying log with a base of e. So similarly here, let's say we wanted to evaluate g of 1. So g of 1 would be taking ln of 1. And so ln of 1 is asking what power do you have to raise e to get 1? And the answer would be 0. So for this function, when the input is 1, the output is 0. And actually, we'll see that for any logarithmic function, it is always going to contain that 0.10 because as we talked about in the last video, every time you take a logarithm of 1, regardless of what the base is, the answer is always 0. And that's just because any number raised to the 0 is 1. But we'll get there a little later. Okay, so I want to jump right into an example of a logarithmic function. And I want to fill out a table and then we'll sketch its graph and we'll make a comparison with another function and see that there's a special relationship between logarithmic functions and exponential functions. Okay, so let's start by filling out this table. So I would encourage you to pause the video and try to fill this out yourself. So it's just like what we did on the previous page where we're just plugging in these numbers. So for example, for 1/4, we would be taking log base 2 of 1/4. And so log base 2 of 1/4 is asking what power do you have to raise 2 to get 1/4? And the answer would be -2. So when the input is 1/4, the output is -2. So similarly, when we plug in 1/2, we're taking log base 2 of 1/2. And so that's asking us what power do we have to raise 2 to get 1/2? And the answer is -1. Then we're taking log base 2 of 1. And so that's asking what power do we have to raise 2 to get 1? And the answer is 0. Then we have log base 2 of 2. So the exponent to raise 2 to get 2 would just be 1. And then finally, we have log base 2 of 4. And so to get 4 from 2, we would have to take 2 and square it. So the answer is 2. Okay, so before we go and sketch the graph, I want to point out that if you look at these inputs and outputs, they should look a little familiar with an exponential function, right? So for this function, when we have an input of 1/4, our output is -2. When our input is 1/2, our output is -1. When our input is 1, our output is 0. And then maybe even, I think these are the ones where it becomes like the most clear. So when we input 2, the output is 1. And when we input 4, the output is 2. And so this is kind of the reverse of an exponential function, right? So let's take a look at making a table for 2 to the x. So let's fill out this table with some values. So let's plug in -2, -1, 0, 1, and 2. So what would we get as our outputs for this exponential function? Well, 2 to the -2 is 1/4, so we'd get 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first power is 2. And 2 squared is 4. So if you look at these tables and, kind of cover up this part in the middle, that was just how we evaluated it, notice that the inputs and the outputs are swapped. And so the function log base 2 of x is actually the inverse function of 2 to the x. So let's sketch both of their graphs and kind of confirm that we see that relationship emerging that we should see between a function and its inverse. Okay, so let's start by graphing the logarithmic function. So it contains the point 1/4 -2. It contains the point 1/2 -1. So 1/2 -1. It contains the point 1, 0. So 1, 0 would be here. It contains the point 2, 1. And then finally, it contains the point 4, 2. Okay, so I'm going to start by connecting the dots, and then we'll, in order to kind of figure out where this function is going on its other parts, like where does it go this way and where does it go this way, let's actually sketch the function 2 to the x, and that will, I think, help us visualize what the rest of this function looks like because they are inverse functions. So 2 to the x, that one we've graphed before, so we know it contains 0, 1, 1, 2, 2, 4, -1, 1/2, and -2, 1/4. So something like this. And then from our knowledge of exponential functions, we know that exponential functions are going to just keep going up and up and up, right? And it also will contain the point 2, 8. And then what happens on the left side? Well, we know that we're going to have a horizontal asymptote, right? So the graph is going to get closer and closer to the x-axis. So this is the graph of our exponential function. So if the function in purple, if the logarithmic function is the inverse, remember that inverse functions should be reflections of each other across the line y is equal to x. And then additionally, the x and y coordinates are swapped. But understanding this reflection idea will help us fill out the rest of the graph, right? So if the exponential function has this horizontal asymptote that goes this way, if the purple graph is supposed to be kind of the perfect reflection over the line y is equal to x, well, then it should have actually a vertical asymptote, right? It should go down like that. Now they're reflections of each other. And then similarly, we can kind of use the green graph to figure out what the shape of the purple graph is. We can also add this point. We know that it should go through 8, 3, right? Because log base 2 of 8 is equal to 3. So what we'll see is that on the right, the graph goes up, but it doesn't like shoot up so steeply the way that the exponential one does. It kind of like goes up slowly, right? So this is what the graph of a logarithmic function will look like. And we'll see that just like with exponential functions, there are two different shapes for logarithmic functions, but this is one kind of a shape that a logarithmic function can have. So on the next page, we're going to write down some key features, but a couple of things I just want to point out to you while we have this graph pictured is, so as we said, the original or the exponential function has a horizontal asymptote, right? And so the logarithmic function instead has a vertical asymptote. So that's one way that they kind of switched from each other. Another thing that you might notice is that the exponential function has a y-intercept of 0, 1. And it has no x-intercept. On the other hand, this purple graph has an x-intercept of 1, 0, right? That's kind of the symmetric point to 0, 1. And then it has no y-intercept because it has that vertical asymptote. And then we'll also write down some things about domain and range when we get to this next page. Okay, so I want to do kind of a general comparison about things we know about exponential functions, things we know about logarithmic functions. So the first thing for exponential functions, we know that there's two general shapes. And so, by the way, one thing I want to point out is that when we talked about exponential functions, I said a to the x. I'm going to, in this video, use b to the x to match with the b from the logarithmic function. And actually, sorry, before we do this page, there's one thing I want to do. I want to go back to our first page and just kind of write down this idea about inverse functions because it's so important. So in general, a logarithmic function f of x is equal to log base b of x is always going to be the inverse function of an exponential function g of x is equal to b to the x. So in other words, logarithmic functions and exponential functions are inverses of each other. That shouldn't be too surprising because if you think about it, they kind of work backwards from each other, right? It's kind of like squaring and taking the square root. Logarithms work backwards to find an exponent, whereas exponential functions take something and raise it to an exponent. So that's why they're inverses of each other. This fact is really, really important to know because it will help you to be able to sketch the graphs of logarithmic functions. So at least for me, I have a much easier, it's much easier for me to remember the shapes of exponential functions, right? Because exponential functions, you can kind of think about how they grow or they go down as x gets bigger. They're just a little bit easier to kind of wrap your head around. Logarithmic functions are a little weird, right? They're kind of, you have to work backwards in order to get the answers. It's just not as intuitive. So if you are super familiar with what the shapes of exponential functions look like, you can just use the fact that they're inverses to figure out what the graphs of logarithmic functions look like. So that's really what we're going to be focusing on this page. Okay, so exponential functions, we know that there are two general shapes they have. So they can either have a shape like this. So this is like the one we just did, 2 to the x. And so this is going to be the shape that you have if the base is greater than 1. On the other hand, if the base is less than 1, you're going to have a shape that goes down like this. So this is the shape if the base is less than 1. And so then in the example we just did, we saw an example where the base was bigger than 1 for the logarithmic function, right? Because we had log base 2 of x. And so what did that look like? That looked like the inverse of this one, right? This is the one where the base is bigger than 1. And so the inverse function ended up looking like this. So this is what a logarithmic function will look like if the base is bigger than 1. And then what about if the base is less than 1? Well, that will just look like the inverse of the second kind of exponential function, right? So this one, I always have a harder time drawing this one, but it would look something like this. And I should mention that it's pretty uncommon to encounter logarithmic functions where the base is less than 1. They're just not used that often. So that would be something like log base a half of x, or log base 0.3 of x. Those are fine. They're valid logarithmic functions. They just don't come up a whole lot. So it's really more important to be familiar with this graph shape than the one on the right. I do want to quickly show you just a picture of like the different ways that logarithmic and exponential functions can look. So what I have here is in red is the function f of x is equal to b to the x, and then in blue is g of x is equal to log base b of x. And then I have b set to vary. So I'm going to move, I did something like this with exponential functions, right, where we looked at, how does the shape of the exponential function change as the base changes. And so just like how the exponential function's shape changes as the base changes, so does the logarithmic function, right? So the bigger the base, the steeper the exponential function gets, and the kind of less steep the logarithmic one gets. And then if I drag the base to be a number that is less than 1, so something like this, well, then we see that the exponential function has that other shape, right? And so similarly, the logarithmic function also has a reverse shape. And then if I try to make the base negative, they both disappear, right? Because as we mentioned earlier, logarithmic functions are also not defined when the base is negative or 0 or 1. So to kind of answer that question about, why is it that logarithmic functions have to have a positive base that's not equal to 1? It's because they're the inverses of exponential functions. So if we have those restrictions on exponential functions, we also have the same restrictions on their inverses, which are logarithmic functions. Okay, so I want to write down a few more kind of key features of exponential and logarithmic functions. So I want to talk about the domain, and the range, and then we'll also talk about asymptotes and intercepts. Okay, so what is the domain of an exponential function? Well, we've talked about how the domain is all real numbers, right? Because you can take an exponent or a number and raise it to any exponent. So there's no restrictions on what kind of numbers you can plug in. However, the range is not all real numbers, right? Because if you take a number and you're raising it to all these different exponents, you're never going to get an answer that equals 0, right? Like imagine you take the number 2, you raise it to all these different powers, you're never going to get 0 as your answer by raising 2 to a power. And so the range is everything up to 0. And we can also see that from the graph, right? Because the graph has this horizontal asymptote, it gets closer and closer to the x-axis, but it never actually touches it. Okay, so what are the domain and range going to be for logarithmic functions? Well, remember that for for a function and its inverse in general, the domain and range are always going to be reverses of each other because we're switching the inputs and outputs, the x and y values. And so for a logarithmic function, the domain is going to be everything bigger than 0. And the range is actually going to be all real numbers. And we can see that from the graph as well, right? Because we have a vertical asymptote at 0, we can see that the domain does not include numbers that are over here, right? You cannot plug in an x value that's negative. You cannot plug in 0. You can only plug in x values that are to the right of the x-axis. And that also makes sense if you think going back to our video from the last video, we had a few examples where I asked you to evaluate a logarithm of a negative number or of 0, and the answer was does not exist, right? There's no such thing as log base 2 of -4 or log base 2 of 0. And that's because the domain starts at positive numbers. You're not allowed to take a logarithm of 0 or of a negative number. Okay, what else do we have going on here? Well, we talked about how with exponential functions, they always have a y-intercept of 0, 1. And they also have no x-intercept, right? Because they have a horizontal asymptote that is on the x-axis. So they have no x-intercept. So for logarithmic functions, that basically all swaps. So instead of having a y-intercept of 0, 1, they always have an x-intercept of 1, 0. And they have no y-intercept because of the vertical asymptote. And those x and y intercepts, if you think about it, they make sense, right? Because the reason that an exponential function has a y-intercept of 0, 1 is because any number to the 0 is 1. And so you input 0, you get 1 as the output. And then logarithms work kind of backwards of that, right? So if you take a logarithm of 1, if your input is 1, your answer is 0, your output is 0. And so that's why the logarithmic functions contain the point 1, 0. Last thing I want to mention is the asymptote. So we know that the exponential function has a horizontal asymptote. And specifically a horizontal asymptote at y is equal to 0, or the x-axis. And then similarly, this logarithmic function is always going to have a vertical asymptote at x is equal to 0. So basically, what I'm getting at here is that this set of information, if you know the one on the left, if you know how exponential functions look and you know all these features of them, you don't need to kind of burden yourself with memorizing a whole nother set of facts. If you understand the relationship between exponential and logarithmic functions, you get all this extra information for free because it just kind of comes hand in hand with the information about exponential functions. Okay, I want to do a few more examples of sketching functions. So we're going to sketch ln of x, and then we're also going to do a couple of transformations of ln of x. So we're not going to do, in terms of transformations, we're not going to do as complicated of transformations as we did with exponential functions. We're just going to stick to some pretty simple ones. Okay, so how do we go about sketching ln of x? So this is my advice in general for any logarithmic function. You could always make a table, that's one way to do it, but I think the easiest way to graph it is to start by sketching the graph of its inverse. Start by sketching the graph of the exponential function that is its inverse, and then you can just flip it over the line y is equal to x to get the logarithmic function. Okay, so which exponential function is this an inverse of? So f of x is equal to ln of x is the inverse of g of x is equal to e to the x, right? And so if we can start by sketching the graph of e to the x, we can use that to find the graph of ln of x. So e to the x, and I should mention that both e to the x and ln of x, even though they're a little more annoying to draw because there aren't as clear of numbers to choose because e is, not a whole number. In spite of that, these are actually really, really important functions to be familiar with. So when you get to calculus, you're going to have a much easier time if you're very quickly can remember what the shapes of these graphs look like. So e to the x, we know has a y-intercept of 0, 1. And then it goes through the point 1e, so that's 1 and then approximately 2.72. And then, might be handy to know that e squared is about 7.4, so that would put a third point somewhere like that. And then we know that it has a horizontal asymptote at x or at y is equal to 0, and then it keeps going up like this on the right. So this is the graph of g of x is equal to e to the x. So what is ln of x going to look like? Well, it's going to be the inverse of this. So if we think about reflecting this over the line y is equal to x, and reversing the x and y coordinates, that will give us the graph of ln of x. So it's going to go through the point 1, 0. It's going to go through the point, instead of 1e, it's going to go through e1, right? So that's about 2.72 and then a y coordinate of 1. And then e squared was about 7.4, so it will go through about 7.4 as the x coordinate and then 2 as the y coordinate. And so this is the general shape of the right-hand side, and then we know that it will have a vertical asymptote like this. So personally, if something comes up when I'm teaching calculus where I need to refer to the graph of ln of x, this is actually how I graph it, or how maybe I'm bringing up just the mental image. To bring up the mental image, I first think about what e to the x looks like, and then it just becomes so much easier to remember what ln of x looks like. Okay, so let's do a couple of transformations. So the first one is going to be g of x is equal to ln of x minus 1. So what kind of a transformation is this? Well, we can see that we're adding or subtracting, and specifically we're subtracting from x. So what happens when we subtract from x, or maybe I'll do it like this. Well, when we subtract from x, that means we're going to be shifting to the right. Okay, so that means we want to take the graph that we have in purple up here, right? This is our ln function, and we want to shift everything to the right by 1. So I'm going to take each of these points, the 3 points that we have, and move them over by 1. So instead of having the x-intercept of 1, 0, it's now going to be 2, 0. Instead of being at e1, it will now be at e plus 1, 1. So e plus 1 would be about 3.72. And then I'm not going to quite be able to fit it on, but instead of being at about 7.4, so e squared 2, it will be at e squared plus 1. So that's about 8.4, and then a y coordinate of 2. Okay, so this is kind of the right-hand part of the graph. What about the asymptote? So just like with exponential functions, when we shift the graph, we have to be aware of if the asymptote is moving. So if we look at the original function just of ln of x, we have a vertical asymptote, right? We have a vertical asymptote at x is equal to 0. And so where is that vertical asymptote going to be on this one? Well, if we shifted everything to the right by 1, the asymptote should be at 1. So here we have a vertical asymptote at x is equal to 1 instead of at x is equal to 0. And so our graph is going to look like this. Okay, what about this one? So h of x is equal to ln of x minus 1. So this time, instead of subtracting from x, we're subtracting from ln of x. So that tells us instead of being a horizontal shift, it's going to be a vertical shift. And specifically, we're going to be shifting down 1 unit. And so that means we want to go back to our original function, ln of x, and just move every point down 1. And so instead of going through the point 1, 0, it will now go through the point 1, negative 1. So we now have the point 1, negative 1. Instead of going through the point E1, it will now go through the point E0, so about 2.72 and 0. And then we had E squared, comma 2. Instead of going through E squared 2, it will now go through E squared 1, so that's about 7.4 and 1. So here's the right side of our graph. And then what about the left side? Well, when we shifted this, we shifted it down, right? And so if we picture shifting this purple graph up and down, that's not going to change the vertical asymptote. So the vertical asymptote is still going to be at x is equal to 0. And so the remainder of the graph will look the same as it did in our original function, and we still have this vertical asymptote at x is equal to 0. All right, so that is it for this video, and definitely check out the worksheet so you can get some more practice with graphing logarithmic functions and some transformations, and I will see you on the next video.